problem solving with exponential derivatives. So let's read our problem. It's relatively lengthy. So on January 1st, 1850, the population of Gold Rush Town, what a name, was 50,000. The size of the population since that can be modeled by the function P at t, P most likely representing population, T in reference to time, is equal to 50,000, which is our starting amount, multiplied by, it looks like a decay rate of 2%, which means it's dropping to 98% of its previous population to the power of t, t being the number of years since the year we started. So this is a decaying town. It's dropping every single year. What was the population of Gold Rush Town on January 1st, 1900? At what rate was the population of Gold Rush Town changing on January 1st, 1900? Was it increasing or decreasing at that time? Okay, so first of all, the first question actually does not involve derivatives of any function. They're essentially just asking us what was the population, so solve P at t. What we have to discover is what the t is in this example. If we're starting at the year 1850 and they're asking for 1900, how many years have passed since that time? 50, very simple. So in this case, t is equal to 50, which means our P at t is population at 50 is equal to 50,000. Multiply it by 0.98 to the power of 50. And try this out. Perfect, you did it for me. 18,208, you said?
Yeah, 0.48.
0.48, so 0.8. Someone that chopped in half. How unfortunate. Okay, so that technically means they're dead. We have 18,208 people in the town after 50 years, so this has dropped quite a bit in this question. Now, B, though, asked us for what was the rate. At what rate was the population of Gold Rush changing? So the rate of change, which means we need to derive the function they originally gave us. So question B, P at t, we'll rewrite the original, is 50,000 multiplied by, what do we got here? 0.98 to the power of t, okay? This is our coefficient, this is our base, this is our variable exponent. So according to our rules, we have f at x is equal to base to power of g at x. That means f prime x is equal to the original, so b times g at x, multiplied by ln of the base, multiplied by the derivative of g at x. So let's figure out what that is in this case. Our original function, we're at now p at t, so we're deriving our function, p prime t. Our original function is this here, 50,000 times 0.98 to the power of t. Our base is 0.98, so multiplied by ln 0.98. And the derivative of our exponent is t. Derivative of t is just the value of 1 in this case, so 1 falls out, and we're left with 50,000, 0.98 to the power of t multiplied by ln 0.98. Now, they wanted the rate of change at this specific year, and at this point, that means p prime t, we're looking at 50. So 50 years down the road, what was the rate of change? We plug in 50 for our value of t. So 9.8 to the power of 50 multiplied by ln 0.98. Anybody have a calculator that can help us out? I'll try it on there. Negative 0.2? 0.02. Okay. 0.02. So the rate of change at this point is 0.02. Okay.
That's just the one.
Oh, you didn't put this all together? Okay, let's do it on a calculator. Instead of yelling out around zero. Okay. 0.98 ln. You got a full answer? Okay. This is not it. Negative 367. So at this time, our population is dropping by 367. So clearly it's decreasing. And we could have implied that because we knew if this was essentially representing a decay rate. So we knew we'd have a decreasing population by the amount of 367 people after 50 years. That would be at the year of 50, yeah, so per year. And then in the 51st year, our rate of change would change again.